Hey everyone, it's Kenny. So if you've ever built an AI agent that works most of the time, or even 90% of the time, or it does well in development but then falls apart in production, then this video is for you. We are diving into human in the loop. It's something that's often overlooked by AI builders and I think generally underutilized in agent systems. And it might just be the missing piece your agents need to actually work in the real world. Today, I'll show you how to implement it in your LangGraph agents. Now, agents are becoming exceedingly capable, especially with all of the MCP tools that they can be connected to, but they can still be highly unreliable and error prone. And for many use cases, especially in production, that's simply not acceptable. I want to start by going over some of the most common failure points in agents that I see and how human in the loop can address those to get us much more reliable agents that work closer to 100% of the time. As we go through these failure modes, definitely let me know in the comments below if I missed any or if there are some special ones that you've run into that are not covered here, and I would love to hear from you guys. Failure mode number one is infinite loops. If you've worked with agents enough, you might have run into this where an agent gets stuck repeating the same failed action over and over. An example where this has happened to me is for SQL query tools where the agent tries to run SQL against a database, but a table doesn't exist or it got the column name wrong, and for whatever reason it tries to fix it, but it just doesn't have enough context or it's just not a good enough model to correct the mistake. And so it ends up trying just a bunch of random attempts over and over, which just burns through resources and it kind of gets stuck in this loop until you either hit the recursion limit or you stop the chat. Failure mode number two is wrong tool call, where the agent doesn't really seem to understand the query that you give it and it ends up calling an incorrect tool. This happens all the time and it's prone to happen even more as MCP servers become mainstream and we're connecting our agents to many more tools. It's just easier for LLMs to get confused. This is where you really have to do a good job of the prompting to let it understand what tools to call and when, and even implement some other guardrails like grouping tools together and only giving it the context for a particular tool group, for example, just to keep things more organized. So human in the loop isn't necessarily the only way that you can solve some of these failure modes, but it is probably the easiest to implement and it's going to give you a lot of bang for your buck. Failure mode number three is where the agent actually does call the correct tool, but then passes the wrong inputs into the tool. On the left, we have the example that we just discussed in the infinite loop failure mode where there's a SQL query and something is wrong with that query. It might be selecting from the wrong table, but you can also have this failure mode happen in much higher stakes tool calls where the agent maybe has a touch point with customers, like in this example on the right. The agent is sending an email to Jane, but it mistakes that person as John. And so in the body, it decides for whatever reason to add the full credit card number for John and maybe some other details that it shouldn't be sharing and sends that out to Jane. So this is the type of mistake that you would want to get ahead of because this can be very costly to you and damaging for your business. Number four is unsafe actions, where you might have an agent that has access to your database and it ends up completely dropping a table or deleting records that you didn't want it to delete. Then you have to go and clean up all that mess if it's even recoverable. Or another example would be of the agent running some malicious code which you don't have sandboxed and it ends up ruining something on your computer or leads to data loss. The last failure mode, which is a little more subtle than the others, is misaligned output. And this is where there's no like tangible mistake. There's no wrong tool call that it makes or an error in the code. The agent just misunderstands the direction that you wanted to go in, and it either goes off on a tangent and does a bunch of things that you didn't really want it to do, or it just totally misunderstands what the end goal was and ends up wasting a bunch of time and resources. A really good example of this is if you use any of the AI coding IDEs like Cursor or Windsurf. Oftentimes you'll ask for something and those models are just so eager to help. They'll create dozens and dozens of files, write thousands of lines of code before you realize, like, no, I didn't want you to do this. I just wanted you to implement some simple function. And then you're slamming on that red stop sign to interrupt the model and then tell it what you actually wanted to redirect it in some way. So misaligned output is, again, it's a subtle one, but it happens all the time. And this can also be addressed with human in the loop. So finally, let's talk about human in the loop. Human in the loop is where an agent has received a task and it's started working on that task, and then we interrupt it at some point and the agent cannot resume its work until it's received some input from a human, from the user. That can be as simple as approving or rejecting a tool call, but you can cover really all of these failure points that we've talked about today, including catching unsafe tool calls, preventing infinite loops, or correcting an agent's direction when it's going off on a tangent, when it has some misaligned output. All of those can really be addressed by human in the loop. Now, how exactly does human in the loop work in LangGraph? Just imagine we are talking with our agent, the graph is running, and all of a sudden the agent decides to take an action or call a tool. We can define within the graph, and of course we'll see this in the code in a bit, but we can define within the graph what tools we want to protect behind human in the loop. And whenever those tools are called, we'll hit a breakpoint. That just means that the graph execution will stop at that point. It'll stop indefinitely until we get input from the human. And so that's where we move from the graph breakpoint to the human review step, where we are going to collect some information from the user, which can either be a message to approve the tool, reject the tool. We can reply back to the agent to give it some guidance, or we can even edit the tool call. There's a lot of things we can do at that human review step where we're passing in some data back to the graph. Once we collect that human review, then we simply resume the graph and it will continue execution from where it left off. So that's kind of illustrated in this really simple diagram. And once the graph is resumed, we essentially just continue through this loop where if we hit another protected tool again, then we would hit a breakpoint and then go to the human review again, and so on. But we're going to get into the nitty-gritty in just a second in the code. Before that, I have to say that human in the loop isn't necessarily a one solution fits all. There's a lot of ways to gain reliability and control over your agents. Human in the loop definitely isn't the only way to do it. But like I said, it is a low-hanging fruit that you can use that's fairly simple to implement, and you can get a lot of mileage with it. But there are other methods for building reliable agents like guardrails and permissions. Guardrails would be, for example, where you're programmatically setting rules to validate tool inputs or outputs. Going back to the SQL tool, if you only wanted the agent to be able to run select statements, for example, then you can have some really simple regex in the tool call where anytime you see an update or delete method in that SQL query, then you just simply return an error and make the agent try again. So that's an example of a guardrail. That's something that we would hard code and prevent the agent from completely making those mistakes ever. So it works 100% of the time. Another example is permissions, where we can restrict the access to the agent. So in the same example, if we had a SQL database, we can create a new role for the agent and assign it to the agent so that any queries it runs, is dictated by the permissions it has, so the tables it can see and the functions it can run, etc. So these two things give you another level of control, and really to build production level reliable agents, you kind of want to play with all of these. But today we're just going to focus on human in the loop. Ultimately, if you want reliable agents, then you need to have human feedback. Today's agents are getting better every single day, and I have no doubt that in the near future, these types of control mechanisms will be used less and less. But I think we're still a ways away from having completely autonomous agents. And a lot of that just has to do with the fact that we're not the best at providing complete context to agents when they're solving some of our problems. So it's something that I highly recommend you spend some time learning and building into your agents. Really quickly, if you are getting value out of this video and you're enjoying it, please consider dropping a like and subscribing for more content like this, where we really try to go beyond the surface level examples and the docs and build some real world AI. And with that, let's get back into it. If you want to follow along, then you can head over to the repo, which is going to be in the description below, and grab that project URL and then go ahead and clone it locally to your computer. Once you've cloned the project, you can cd into the directory and open that in your code editor. And the first thing we're going to do is set up our environment variables. So you can click on .env.example, and there's going to be 3 keys that we need to set up here. One is your OpenAI API key. I wrote required here because we're using that as our LLM provider, but if you do want to, the project is set up to work with Ollama. So if you do have Ollama set up locally, then you can pull a model that's compatible with tool calling, and then I'll show you in the graph.py how to configure it for using Ollama locally. The next thing you want to set up is the workspace. So this I recommend just setting to the current project directory. And the easiest way to do that on Mac, and it should be similar on Windows, is to right click the pyproject.toml file. And this is really just to get the path. So you're going to click on copy path to the project root directory. So once you have that, you can paste it into the workspace, and we're just going to delete the project name from it so that you just have that project directory set. Finally, this last one is optional, but I do always recommend setting up tracing for your projects. You can head over to smith.langchain.com to get a free Langsmith API key. And once you're done with that, you're just going to want to rename this file, save it as .env. I've already done mine here, but just make sure you get rid of this .example at the end, and then the environment is all set. Next, you're going to want to open up a terminal, and we need to install our dependencies. Now for this project, we are going to be using Docker. So if you don't have Docker installed, then first head over to the description to get the URL to the Docker homepage and go ahead and install Docker Desktop first. And then we're going to be using the UV package manager. So I also recommend installing that. The link will also be in the description. Once you've installed those two, you can come back to the terminal here in the IDE and run the command uv sync. That's going to set up a virtual environment within the project directory and install all of the dependencies. And then you're also going to want to run the command uv pip install space -e space dot. And that's going to install the current project as a package so that it just helps us import things easier. The project is set up to be a monorepo. This is typically how I like to scaffold my agent projects. You have a front end folder which just has a simple chat.py file, and that allows us to chat with our agent. All of the agent code actually lives within the source folder, and if you had multiple agents, you can have multiple folders in here. I just have one called goop, so that's my agent. And then in here is where we have our graph.py. This agent has access to the file system MCP server. So opening up my mcp config.json, If you're not familiar with MCP and how we set that up for our agents, then definitely go watch my video on how to use MCPs, why it's important, and how you can set it up with your LangGraph agents. Those links will also be in the description. Here we're just defining a Docker run command. So this is spun up in Docker, and we have an environment variable here where we're specifying the workspace. So that is the environment variable that we configured in our .env file, and that sandboxes this MCP server where the agent can only read files, write files, etc. within that specified workspace. So in this case, it's our project root. And that's the only set of tools that we're giving to our agent. Popping over to the file system MCP server on GitHub, here you can actually see what tools this MCP makes available. So you have the ability to read and write files, to create and manipulate directories, search files, etc. So some of these you can see are sensitive tools like writing files, deleting entire directories. Some of these more sensitive tools we're going to want to add human in the loop just to have that control and prevent some of those issues that we talked about earlier. However, other tools are completely safe to run and are read-only, like reading files or searching files or getting file metadata. And so we're going to configure it to where only certain tools are protected by human in the loop. Now coming back to the code, we're going to open graph.py and inspect how we've defined our agent here. So the first thing we want to look at is how we've defined this agent state. And if this doesn't look familiar or you need a refresher, I have a video on a complete guide to LangGraph, so go check that out. Here we're defining our agent state with 3 attributes. You have messages, which is going to have our conversation history. And then we have a list of tool names called protected tools. And these are the tools that we are going to require the agent to get human approval from. So you can see I have create directory, edit file, move file, and write file. The last attribute is a YOLO mode. This is exactly what it sounds like. If you're familiar with Cursor, which also has a YOLO mode, it's the same thing where it's simply a Boolean. If it's set to false, then human in the loop is on. So any time we call one of these protected tools, then the graph execution will be paused for human input. If on the other hand it's set to true, then we simply ignore a protected tool list and then call any of these tools automatically. Next, moving on to the graph, we have a pretty simple graph here. We're going to first connect to our MCP and grab those tools. This is where I mentioned you can either use OpenAI or Ollama as your LLM provider. So I've just commented this section out. And I want to call out that I've explicitly set parallel tool calling here to true, where I've talked about in previous episodes. We want to set up our tools as async functions so that they can be called in parallel, and it really unlocks the speed and processing power of your agents when it comes to tools. But I just want to call this out so that you can keep it in mind. We're going to come back to it later, and I'm going to show you how parallel tool calling gets a little tricky with human in the loop, since you do need to get approval for each tool. So human in the loop doesn't just work out of the box with parallel tool calling. You have to do a little bit of extra work to get that to work. But again, we'll revisit this later. It's more of an advanced topic. Moving on to the assistant node, it's exactly what you'd expect. We're invoking a response from the LLM based on the current conversation history and then adding that response to the state. So that's nothing new. The new part is this human tool review node. So let's spend some time to really understand this method. The first thing we do in this node is to look at the last message, and we're going to do a quick check to make sure that the last message is an AI message type, meaning it came from the AI and not somewhere else. And we're also going to ensure that there was at least one tool call in that last message. If not, we're going to raise an error. Then we're going to grab that last tool call and we are going to call this interrupt method. This interrupt method is really the meat and potatoes of this whole thing. There are two new primitives that are really important to understand when it comes to human in the loop in LangGraph. One of them is this interrupt method and the other is this command object, which we'll cover in a bit. I'm just going to go into this interrupt method where it's defined in the library so we can kind of look through it. So essentially it interrupts the graph with a resumable exception. So it's going to throw an exception, which is a type graph interrupt, and LangGraph is going to catch that. And so when it sees that there's this exception's been thrown, the graph is going to wait and it can only be resumed. So here you can see a client resuming the graph must use the command primitive. And again, we're going to look into what that command object actually is, but once it's received this command object, then it will continue the execution. And going back to the graph, where you define this interrupt is extremely important. Since the interrupt is defined at this human tool review node, when the graph is interrupted, it will be paused at this node. And once the graph is resumed, it will resume from this same node. But it's going to execute the node completely, so it's going to come back through all of this code. And so there are some funny things that can happen. So for example, if you had some code up here where you're making an API call or doing something else to the state, that would be ran again when this node is resumed. So it's just important to remember where you set this interrupt within this function is important, since all of the code before it will be re-executed a second time. In this case, it's just looking at the last message and looking for that tool call, so that's totally fine because that's still going to be there. Now, another thing I want to mention about this interrupt method is if we look at the type definitions here, you'll see that it takes a value as an input, and that could be of type any, and then it returns a type any as well. So that's up for us to define. In this case, the way that we are calling it is we are passing in a dictionary. You could pass in a string, you could pass different types of objects, again, because it's of type any. Now, the value that you pass into the interrupt, where LangGraph is just calling it value, that value actually gets passed to the client, or where you're calling the graph, where you're invoking it. For us, that's going to be in this chat front end file. So typically it's nice to define it as a dictionary because it's just an easy way to organize the data. So on the client side, when we receive this dictionary, for example, we can access the key message and then print that out to the user. And separately, we can access this tool call in the dictionary and have some pretty formatting around that as well. So passing in a dictionary is a convenient data type for this interrupt value. What you get back from the interrupt, again, is also in any type, and here we are specifying that the return type should be a dictionary. This is important for data validation. You just want to make sure that the value that you're getting back is the correct type that you know how to handle and parse. So it'll become more clear what I mean once we get over to the chat file. And to have a complete understanding of how you implement human in the loop, you really have to understand how we're defining it on the agent side within our graph, but also how we're interacting with the human in the loop mechanism using the interrupt and the command on the client side, meaning in the chat, because that's really where we're getting that input from the human and handling all of the review part. Once we get back our dictionary called human review, then we're going to look for two keys. And again, we're just ensuring on the client side that we are passing these two exact keys to this interrupt. And the first is the action, and the second is the data. By action here, we mean one of 4 possible actions that we are defining. And those are to either continue with the tool, to make an update to the tool ourselves. So if we wanted to change something manually in the tool call, we can update those arguments for the tool call ourselves. You can also provide feedback to the agent, and so that's going to be a natural language response that we pass back to the agent. An example of this is I had a CRM agent that was responsible for drafting emails to customers, and before sending out those emails, I might give the agent feedback on its draft and say, hey, add some more emojis or add some humor to this, and then it would go and revise the email. So that's an example of giving feedback where we're not changing anything about the tool call. We're just letting the agent know that we have some input and having it make some adjustments. And then the last one is to simply reject the tool. So those are the 4 actions that we can accept, and we're going to capture those in this variable here. And then certain actions are going to require data, so additional information from the user. Continue, for example, doesn't require any data. So if the action is to continue, we simply will route to the tools node and go ahead and execute the tool. And we do that with the command object. So let's take some time to dissect and understand the command primitive. The command is a special class that you're always going to use in conjunction with the interrupt method. First, you have graph, which can be the name of the graph that you want to go to next once you resume execution of your agent. So this is really used for multi-agent systems where, let's say you have an orchestrator agent, and the orchestrator agent has multiple subgraph agents. Then you can resume the execution depending on the logic that you've defined here in your interrupt method, which subgraph you want to call, so which agent you would want to route to next. So to do that, you just pass the string name of that graph. The next one is update, and this is to update the state. So you can pass in a dictionary with the specific keys that you want to make updates to. Then you have resume, which is only going to be used on the client side when we want to resume execution of the graph after we've hit an interrupt. And then finally, you have go to, which is just going to specify the string name of the next node that we want the graph to go to once we resume it. Let's walk through this so that we can see this in action. If our review action is to continue, we're going to return a command with a goto variable set to tools, and that's going to route us to the tool node for that tool to get executed. If instead our review action is to make an update, meaning we want to change an argument in the tool call, then what we're going to do is first construct a new AI message, and we're going to use the same content from the last message. So remember, the last message is the AI message in which the AI decided to make a tool call. But then we are creating a new tool call with the same tool call ID and name, but this time where we're adding in the new data that we're getting from that human review. And again, that's going to come from the front end, from the client. When we resume the graph, we're passing in this data key, and we're going to use that to make any adjustments that we want to the arguments of this tool. Importantly, we have to set the same ID from that original AI message where we called the tools as our new ID here. And whenever you do that, it simply replaces that previous message with the new message at the same ID. Once we've constructed that new message, we're calling it updated message. Then this time when we return the command object, we're specifying that we still want to go to the tools and go ahead and execute this tool, but now we're making an update to the messages key with our new updated AI message that's going to have our new arguments for the tool call. So that's how you handle updates. With feedback, we're also going to have to collect data that's being passed in with the data attribute. And what we're going to do is create a new tool message. So this is essentially the tool response to the tool call. And as the response, we're adding in whatever input we want from the client as the content, and then adding that tool response to the messages key, again using the update variable. Notice in this case, we're actually routing back to the assistant because we want it to read our feedback in that tool message and then decide whether it's going to execute it again based on our input or just follow whatever direction we've given it in that tool message. The last action, reject, if we want to reject the tool, we're going to take a similar approach where we're going to construct a tool message or a tool response. And here you can see that I'm just writing in my own message. I'm saying the tool call was rejected by the user, follow up with the user to understand why and how they would like to proceed. And then we're going to again call that update messages key to add this new tool message and send that back to the assistant. So now the assistant is going to read this tool response and then act accordingly. Finally, this is just a catch-all. In case there was no input from the human, maybe an empty string was sent in, we're just going to go ahead and assume that that's continue and use the command to send the graph onto the tool node. Hopefully it makes sense how we're using the interrupt and command primitives in LangGraph to handle these different conditions of human input. Now we still need to implement the logic for when we actually go to this human tool review node. And that's where the assistant router comes in. So normally you wouldn't have any of this code here. You would just have a condition of just checking whether a tool was called in the last message and sending the graph to the tools node to execute that tool, or routing to the end and responding to the user directly if there was no tool call. This is the new part here where we are going to first check if YOLO mode is off, and then if it is off, we're going to iterate through all of the tool names. And the reason why we're iterating through all of the tool names is because if we have parallel tool calling on, then you could have more than one tool call present. But we're just going to check if any of those tool names are within our protected tools list. And if it is, then we are going to route to the human tool review node instead. So let's see what the logic looks like by inspecting the graph. So we can go ahead and just hit Shift Enter to run this. So this will probably look pretty familiar to you, except for maybe the human tool review node, but we just have a simple tool calling assistant. The assistant has three options for what it can do. It can either go to the end node, in which case it's responding directly to the user, or call a tool directly where we go to the tool node to execute that tool and then give the response back as a tool message to the assistant. Or if it is in the protected tool, that'll be caught by our router, and that will be routed to the human tool review node where we'll collect that human input. If it is reject, for example, or we want to update, or we want to give the agent feedback, we'll add that tool message and it will be routed back to the assistant node. Or if we go ahead and continue with that tool call, then it will be routed to the tools node instead. So hopefully that gives you a good picture of how we would adjust our graph definition to implement human in the loop. Now let's see the other side of this, which is just as important. How do we handle getting the human input data on the client side? So I've opened chat local from the front end folder, and I'm just going to open this to the side so that we can see it with the graph side by side. I want to focus on just the main loop, which is going to have our while loop for chatting with the agent. And we're going to see how this is different from your typical agent chat loop. First, as usual, we're going to import our build graph method from graph.py, and we are going to configure this, setting a maximum recursion limit. So this recursion limit is where we protect ourselves against that infinite loop. Once you hit 25 node executions, then this graph will simply error out. We're also going to define our YOLO mode here as false, so that we are requiring human input and then passing that in through the initial graph input. So here's our state with the 2 keys. And then we are going to invoke the graph. And I want to walk you through this step by step so you can see how it actually works. So we're going to bypass the while loop and just go through this manually as if we were going through the while loop. So the first thing I'm going to do is actually go ahead and execute this code up here in interactive mode. I'm going to go through the setup here for the graph and then invoke the first step from Goop. So we get a message from the assistant. And then the next step, once you invoke the graph, is to check the state of the graph. And you do that with this graph.getState method. And it's important that you pass in the same config because you need that thread ID to track the specific state for this graph. If we execute that and look at the thread state, so this is a snapshot object, and it's important that when you construct your graph, I went ahead and made a note here, you always have to define a checkpointer in order to enable human in the loop. And that's, again, because we're going to leverage these snapshots. When we interrupt a graph, we're going to save that snapshot, and then we're going to resume from that snapshot once we've collected the data from the user. So checkpointing is required. Now we can check that thread state for interrupts by calling the .interrupts attribute. So if we just look at that, you can see it's empty. This is a tuple. Since there are no interrupts, you basically bypass this whole loop here, and you get to the user input as usual down here. And so we can go ahead and just exit this, and I'm gonna say create 3 poems about Trump, Elon Musk, and Hillary Clinton, and save them separately to markdown files. Okay, so we've collected the input. We can go ahead and execute the rest of this. There's the printout of our input, and then we're going to go back to the top. So in the while chat loop, we would then go ahead and execute the streamed response again. And so we'll see that, that's really weird. It actually didn't call the tools. It just said it was going to, but it didn't. I'm going to come back down here, and then I'm going to respond to it again and say, do it, create the files. And we'll go ahead and print the human response, and now invoke that again, and then hopefully it's able to call the tools this time. Let's see. Okay, so it's called the tools. Now what I want to do is check the state again and see if there are any interrupts. And sure enough, here we see that we have 1 interrupt value, and you can see that it is its own class. There is an interrupt class. This is the value that we talked about in the interrupt method that we defined in the graph, and this is the dictionary that we were passing as the value in the interrupt function. So you can see the key for message. This is the message that we wrote to the front end, and then you have the tool call with the arguments. So now, since this tuple is not empty, since there is an interrupt, we're going to enter this loop here, and this loop is set up to iterate over all of the interrupts in case there are multiple interrupts that have been triggered by the time we get to this point. For each interrupt, we're going to go through, and we're simply going to print out that interrupt. And now this is where we're going to collect the data from the user. we're just setting some placeholders for the action and the data. And then we're going to use the input function to collect the action. And we're just making sure in this loop here that the user is selecting one of the available options, which is either to reject, continue, update, feedback, or exit. So there is an exit point here if the user just wants to terminate the program. But once we have that action, we're going to do a quick check. If the action was either update or feedback, those are the ones where we need that extra data. For update, we would need the updated tool arguments from the user. And if it's feedback, then we need the feedback from the user. So we go ahead and collect that here. For this one, I'm just going to go ahead and say continue to move through it. I just wanted to show you what the state is actually returning and how we're checking to see if the graph has been interrupted and handling the human input. Finally, the last step, once we've collected all the data that we need from the user, is to resume the graph. And so once again, we're going to call our stream graph responses method, which is defined at the top of this file. And rather than just passing in your normal user message like we would, we're going to pass in a command object. And this is where we talked about using that resume parameter, which is going to signal to the graph that we want to go ahead and resume from that interrupt exception. The resume value is the data that we're going to pass back into the interrupt method. So if we flip back over to the graph, maybe put it side by side here and scroll back up to where we had the interrupt. This interrupt method is going to get the data from this dictionary that we're passing back into the resume value. And so that's going to get assigned to human review. And now you can see that we have to be sure to specify the action and the data keys here and ensure that those are consistent with what we're trying to access here in the graph. Once we do that, then the graph simply continues on to the rest of this logic in the human tool review node. And finally, once we've resumed the graph and we stream out the rest of the response from the agent, we are just simply going to get the latest thread state again. So we're going to update our thread state variable, which will have changed. And if there was only one interrupt, then this interrupt will now be gone. And so when we get back to here, we won't find any interrupts. And so the graph will simply continue on to getting the next user input like normal. And that's really it. So I want to show you how this works in real time. So I'll say, hi, what files do I have? It goes ahead and lists all of my files. Now I'm going to say, create 3 poems about Trump, Elon Musk, and Hillary Clinton, and save them to separate README markdown files. So those tools get called. There are 3 tools that were called. And then here's our printout for the human approval step. Once again, we have that dictionary that we specified in the interrupt function. So we can see what all of the arguments are for the tool that it's calling. And I'm just going to go ahead and say continue. Because I pass in the word continue, then it's able to go ahead and get that done without needing to collect that additional data from me. And we can inspect in our workspace, and we can see here that there are the new markdown files that it just created with those poems. So I asked it to create a few more poems for me, and now I've restarted the chat, and I want to ask it to first list all of my files, and I'm going to ask it to go ahead and delete all of the markdown files. And so here you can see what I mentioned before, that this kind of breaks down with parallel tool calling. The agent is trying to move all of these files to the trash folder. We have 6 or 7 markdown files, and it's trying to move them all to the trash file, but all of those tools get called in parallel in the same AI message. And then we're going to that human review node and calling the interrupt method only once, and that's going to show up for the very last tool call that we made. So this doesn't really work out of the box for parallel tool calling. You have to do a little more work to get it to work with parallel tool calls. You can imagine how that might be a little tricky if you have, for example, an agent calling 100 tools in parallel and asking for the human to review every single one by one, versus just showing it maybe all of the tool calls in some aggregate way and asking it to approve all of them at the same time, or however you want to handle it. So it's more of an advanced topic. We're not going to cover it today, but I'm going to show you what happens if I try to reject this tool. So we get an error, and it says the following tool call IDs did not have response messages, and then you have a bunch of tool call IDs. So what's happening here is that we are only handling the very last tool call. As you saw, this interrupt is going to surface the very last tool call, but the rest of the tool calls don't get handled properly. And then so in LangGraph, if you go back to the assistant to generate another response, but you haven't properly closed these open tool calls by providing tool messages, then you'll get this error. So one way to prevent this is simply to deactivate parallel tool calling, and you would do that in your graph.py file by coming down to where we called this bind tools method. So this is a LangGraph method, and you're just going to want to set this parallel tool calls to false. And so that's why I had it explicitly defined here, so you can go ahead and toggle that, and that would get rid of those errors. That is going to do it for today's video. I hope you guys have a better understanding of human in the loop and why it's such an important design pattern and fundamental piece of AI agents, especially if you want to make them more consistent and reliable. If you're interested in getting your hands on the slides that I went over today, feel free to sign up for the waitlist for my free community in the description, and you will get access to these slides along with a really amazing community that I am in the process of building. It's going to have a ton of resources just like this, plus free tools and a ton of other people that you'll be able to work with and collaborate and learn from and help in building these AI systems together. So definitely check that out. And if you learned something from this, if you got value, please give the video a like and share it with your networks and subscribe for more future content like this. Thank you guys again so much for watching and supporting this channel, and I will see you in the next one.